Hey guys, welcome back. We're going to start RLC parallel circuits, but before we start RLC parallel, we got to do a little bit of review of level 1 for a minute so that we remember, how parallel circuits work in level 1. And I've got a little sketch here of a parallel circuit here, 50 ohms, 25 ohms, and 20 ohms. We're going to talk about the rules for parallel circuits in general, and then we'll talk about, calculating the total resistance of the parallel circuit so that we're all straight on how parallel circuits work, okay? So first rule for parallel circuits is there's only one voltage. On a series circuit, there was only one current. On parallel circuits, there's only one voltage. So in this particular parallel circuit, and these are just resistors, this is a level 1 question, level 1 review. 100 volts here, that means there's 100 volts here, 100 volts here, 100 volts here. Okay, so that's the first rule. There's only one voltage. Every load gets the same voltage. Now, this one is a really important one, okay? The total resistance of a parallel circuit is not the sum of the resistors. It's kind of a non-rule, all right? It is a negative rule. RT is not going to be 75, 95 ohms in this circuit. It's going to be something else. In fact, it's going to be less than 20. We'll figure it out in a minute, but I want you guys to put a star by this one, all right? Another rule for parallel circuits is this one right here. The total circuit current is going to be the sum of the three currents, right? And that's the rules for parallel circuits. Now that we've got that straight, let's see if we can calculate RT for this for a second here. Now, this is the reciprocal formula, and it was used in level 1 to calculate the total resistance of a parallel circuit, and I've got it kind of transposed right here. RT is equal to 1 over R1 plus 1 over R2 plus 1 over R3. And so I'm going to calculate RT here for a second. Maybe I'll put my calculator right here where there's no glare on it. Right there, maybe, something like that, okay? And if I wanted to calculate RT in this circuit, I'm going to do it using the 1 over X button, all right, guys? So it would be 50, 1 over X, plus 25, 1 over X, plus 20, 1 over X, equals, and then hit 1 over X one more time, equals. And according to this calculation here, RT is 9.09 ohms, okay? And that makes sense because we remember from level 1 that the total resistance is less than the lowest resistor. All right, guys? So it should be less than 20 ohms. So I believe that this is true. Now, there is another way that we could calculate the total resistance of this circuit without using the reciprocal formula or the other two formulas that you learned in level 1. Which you've forgotten by now. And I'm not even going to go there, all right? The method that I'm going to use to calculate the total resistance of this circuit is this one right here. What I'm going to do is calculate the current here, the current here, the current here, add them together to get the total current, and then apply Ohm's law to the entire circuit to see what the resistance is. So if I wanted to do that, I, for this rung, is going to be, E over R, 100 over 50. So it's going to be 100 over 50, which is going to be 2 amps. All right. On this second one, I is going to be E over R. So for this one, it's going to be 100 over 25. And so for this one, it's going to be 4 amps. And this last one, I, is going to be 100 over 20. And so it is going to be equal to 5 amps, okay? And since this is true here, I can calculate I total. I total will be 2 plus 4 plus 5. So what is that? 9, 11 amps, all right? Now that I know that my current is 11 amps in this circuit, I should be able to calculate RT using Ohm's law. It is going to be ET over IT. And ET is 100, and IT is 11. And so if I try that for a second, 100 divided by 11 equals, it says that it is 9.09 ohms, all right? So what I'm showing you here is so you don't feel like using the reciprocal formula, you could calculate it using the currents, adding the currents, and then applying Ohm's law. And that is how we're going to do it when we do RLC series, or RLC parallel. All right, guys? So give me a second. I'm going to switch out this page with an actual RLC parallel circuit. This, by the way, comes right from Unit 4 handout 5A. It is number 1, and we are going to solve it. Now, have a look up here. It says calculate Z. Z is going to be the sum of all the gadgets in the circuit that limit current. Now, this is a parallel circuit, so there is no such thing as an impedance phasor diagram for this circuit, okay? There's no circuit or drawing that has 3 on the bottom and 6 up and 4 down and then 2 left over and then Z being there, because that would be the same as just adding these resistors here together, okay? It is not this plus this plus this, and it is not even the phasor sum of this plus this plus this. So I need you guys to get that out of your head, okay? You will never, ever use an impedance phasor diagram to solve a parallel circuit. And if you do, it's going to be wrong. Wrong, wrong, wrong. Just as wrong as saying that this is 95 ohms. All right, guys? So don't do it that way. So how are we going to do it? Well, the way we're going to do it is calculate the currents and then add them together and then apply Ohm's law. Now, I want you to notice that I didn't give you a voltage here. And if that occurs, you get to dream one up. And so we'll just use 100 volts in this circuit to figure it all out. Now, if you used 50, you're going to get the same answers as I do using 100. So don't worry about it. Pick any voltage, put it there, and figure it out. If the circuit came with a voltage, use it. If it doesn't come with a voltage, dream one up. I'm going to dream up 100 volts. Okay. So the method we're going to use to solve this circuit, guys, is we're going to calculate the currents and add them up. And if this is 100 volts, then this is 100 volts, so is this, so is this. So we're going to call this IXC. It is going to be 100 over 4, okay? And so I think that's 25, okay? 25 amps flowing in that one. We're going to call this one IXL. Since it's an inductor, it is 100 over 6, all right? So I think that's 16.67, 100 divided by 6. 16.67 amps. We're going to call this one IR. It is going to be 100 over 3. All right, guys, so 33.333. Yep, 33.33 amps. Okay, so now we've calculated our 3 currents. We are going to add them up and then apply Ohm's law to this circuit. Now, unfortunately, these currents can't just be added up directly, because this one's leading by 90, that one is lagging by 90, and this one is in phase. So if we're going to add these currents together, we have to do it using phasors. So I'm going to draw a little phasor world over here where I can add those phasors together. But this is a parallel circuit, and so instead of comparing everything to the current, I'm going to compare them all to the voltage, because I don't care what the circuit is. You always compare your phasors to what is constant between all the items in the circuit, okay? So same voltage everywhere. Let's calculate these currents, or compare these currents to the voltage. Okay, we're going to draw this one first. Always start with the resistor. 33 amps. It is in phase with the voltage. Here it is. This is IR. Resistors always cause the current and the voltage to be in phase, so I'm going to draw them right on top of each other. All right. Next up, we're going to draw, I don't know, doesn't matter which one you draw next. Let's just go with IXL. Now here's the weird thing. When we were drawing series circuits, guys, we were drawing XL up. That's because XL was here and this was current, and I had to draw it so that the current was lagging. Now I'm actually drawing the current. This is an inductor, so that current, that 16.67, needs to be drawn lagging the voltage by 90. And if I draw a phasor that's lagging this by 90, it's going straight down. Okay, so that 16.67 is down or clockwise from the voltage, but I'm going to move it tip to tail. Okay, so this guy right here, this is IXL. It is 16.67 amps. Now, last phasor, 25 amps. That is a capacitor. Capacitors cause the current to lead. Leading phasors are drawn counterclockwise, so it actually goes straight up. And since it has got to be drawn tip to tail, I'm going to move it down here. It is 25 long, so I'm going to draw it even longer than this one. This is IXC, guys, and it is 25 amps. This business here, we're going to call IX, okay? And it is the difference between IXL and IXC. I can't fit it in here, so we'll do it right over here. IX is going to be equal to 25 minus 16.67. 25 minus 16.67 equals 8.33 amps. All right. Now, the sum of those three is going to be a phasor that starts at the beginning of the first one and ends at the end of the last one. There it is. And this is I total. Okay? And I total will be the square root of this plus the square root of that. So I'm going to try that. It is going to be, let's calculate it right over here. All right. I total is equal to square root 33.33 squared plus whatever that is, 8.33 squared. All right, guys, so let's try that. 33.33 squared plus 8.33 squared equals root equals 34.36 amps. 34.36 amps. Now, we haven't answered any of these yet, and I'm going to answer them in the next video. So we'll stop here. You can start the new one now.